We have been go through the topic of convergence and sequences, especially for sequences for 2 lectures from now. So after we talk about the real number system, our focus is about sequence. And today we'll continue the topic of sequence and the convergence too. And previously I was thinking about, well, we can do convergence and sequence in just like 16 minutes, but later I found out, well, it's impossible. It's too many theorems and too many prerequisite knowledge that requires us to look it very carefully. So this is the third one, and I think it will be the last one if I can talk all the 8 pages of content today. And next lecture, we'll start talking about the continuity of functions. So there will be some materials closer to differentiation and integration. Okay. So the first example I'll give today is about a special form of sequence. It's in this form. So it's in the form of like the power of a fixed real number, which is a constant. And it has some interesting properties. For example, if the c is equal to 1, then what the sequence will look like is 1 to the power of 1, 2, 3, 4, 5, 6, and it's always be 1. So it converges, right? And this is the case 1. This is the case 1. And case 2, we have talked about if c is a negative 1, then what will happen? If c is negative 1, then the sequence will become like negative 1 to the power of 1, negative 1 to the power of 2, negative 1 to the power of 3, and it goes on. It will look like that form. And one interesting about negative 1 is like that. Negative 1's even power will be 1, and odd power will be negative 1. So it becomes negative 1, 1, negative 1, 1, negative 1, 1. Okay. And what this is actually means is like, well, it is a sequence that does not converge, that actually diverges. And this is what we discussed in the previous lectures. We can show like it doesn't exist an epsilon that is that negative 1 and 1 can be in the same interval, like a plus epsilon and a minus epsilon, so that fails to be converged. Okay, and some other cases is also worthy to explore in this case. What about like this is 1, this is negative 1, and this is fixed values? What about c is varied? What about c is a variant? Is a variable. So we can also separate it to discuss 2 cases. First one, let's say the absolute value of c is always greater than 1. Then, well, does it converge? Does the sequence here, this one, will this converge or not? Well, let's see. If it's larger than 1, then the c to the power of n is some value of like 5 to the power of 1, 2, 3, 4, 5, 6, and it increases very rapidly because this is a exponential function, right? This is an exponential formula in the terms of the sequence. So, and we can also like for all of the m, which is a real number, and we can find like c to the power of n is always larger than n, and we cannot find the upper bound for such a sequence. And then we can say, well, if it's not bounded above, and because we know the theorem that every convergent sequence is bounded above or bounded, then c to the power of n is unbounded and divergent. So which means like if in this form, and if the c absolute value is greater than 1 and it's divergent, what about the opposite case? Like if the absolute value of c is smaller than 1, then what will happen? Because we have to discover equal to 1, greater than 1, equal to negative 1, which is like also the absolute value is 1. What about smaller? And we'll have the following theorem. If c is a real number and absolute value of c is smaller than 1, then the sequence, the limit of c to the power of n is 0. And because its limits exist, this sequence, when the absolute value of c is smaller than 1, is convergent, and convergent to 0, absolutely. So let's give a proof of it to see it's actually working. So first, suppose like c is a positive number, And well, this might be misleading because we cannot ignore the case that C is actually 0. But we can first see this point, like if C is 0, then it converts to 0 absolute because every term in this sequence is 0 to the power of 1, 2 to the 4, is always 0. So yeah, so it's converted to 0. And what about like C can absolute value of C smaller than 1, greater than 0? Why? So like which means like 0. In the 0 case, we ignored it. What about negative? So C can also be in the range, like you can have two cases here. So the first one is like 0 smaller than C smaller than 1, which is what we discussed here. And also, well, C might be between 0 and -1. So what about that case? That is worth to discuss too. So we'll first see this case and then to see, well, what that means. Okay. So first, remember from last lecture, we have talked about the monotone convergence theorem, which means like for every like sequence that is monotonically decreasing or increasing, then then we can always like say it is converged if it is bounded, right? So let's use this theorem. So when this case, like this is a multi-decreasing sequence, so it must converge to some B. And this is the, and also what the B is, we know it's like it is the infimum or like infimum, or we can say like the least or the greatest lower bound of the CN set. So we know, well, B exists. And now because C to the power of n is equal to C to the power of n plus 1 divided by C, which these are equal. These two terms are equal. And this is larger or equal to B over C because B is because we know like B is the lowest possible of all of the C to the power of n. So this term must be larger or equal to B, and C is equal to C. So this is larger or equal to, and they're all non-negative. So we can do that. Okay, so what this means, like for all of the index that C to the power of n is larger or equal to B over C, and this is another lower bound of C to the power of n. Remember that, right? And because B is the largest lower bound, and this one is another lower bound of C to the power of n. And what we can find out is like this one is greater than B. Why is that the case? Because C is between 0 and 1. So it divides a number which is smaller than 1 and a non-negative, which means like this one is it's greater. This term is greater. So B, well, B is not the largest, it's not the greatest lower bound. B over C is larger than that. And it's still a lower bound, so which is a contradiction. So what this gives us is like, well, B must be 0. Because here we assume like B is not 0. B is not 0, so we can say this is greater. But if B is actually 0, then what will happen is like 0 divided by some C is 0, 0 and equal to B. So that solves this contradiction. So it has to be 0. Okay, so the first case we have already proved that if like if the C is between 0 and 1, and the limit of the sequence must be 0. And what about the second case? Like C is between -1 and 0. So this case, we use a very clever strategy. We'll use this strategy. We say, well, the absolute value of C to the power of n is equal to negative C to the power of n's absolute value, which is equal. And when we are plugging this one to here, which means like, well, if it's negative C, and we can do a negative sign of it. Like if this is negative, and we can do a negative sign of it to turn it positive. And because it is still the same, so it matches with this condition or this condition. So it will also works. Okay, so that's our first finding today. We found like if you ever see a sequence which is in this form, we can like very quickly to discern whether it's convergent or divergent, and yeah, when it is a real number. But when C is not a real number, well, say it's a complex form. It will be very hard to discern it out to see, well, it's actually decreasing or uh, is actually convergent or divergent. It's very hard to say. Okay, so this will lead us to the next theorem, and I would say this is not a very important theorem, but it has some very strong meaning to the real analysis part. Okay, so for all of the n, index n, an and bn is in R, with an is smaller than bn. We can define an interval. In is the closed interval from an to bn, which makes sense because an is always smaller than bn. So this is a correct definition. This is a correct definition. Okay, and for all the indexes, what will happen is like n plus one is a subset of in. Okay, well, so it means like in might be that and becomes smaller and smaller or equal size because it can be the same with a subset and gradually becomes small and remain the same, but it's always decreasing the size, like monotonically decreasing the size, right? And the limit of bn minus an is 0, which means like, well, eventually they will meet the same point because the limit, like this is an, this is bn, and when it goes to infinite, it will be the same point. So this is our assumption. Then what will happen is like there exists only one. This is like means there exists a unique x in the range of in such that for all of the index n, both an and bn converges to x, which means like this sequence converges to x and this sequence converges to x, which actually makes sense because finally they're just one point because it's 0, so it will be the same point. Okay, then how to prove this one? So this one can be a little bit like hard to consider at first what it actually means. So I draw a graph here. So the graph here represent, well, this is a and bn, right? This is in. Maybe we say it's the largest set and most formal set in our discussion because n is smaller one. And when it becomes n plus one, it goes more center to the center, and with n plus 2 and is more centered, and finally will reach x in the real number line. Okay, so there's several things we need to prove here. So the first thing we need to prove like an and bn are convergent. This is the first one thing we need to prove because first we don't know whether it's convergent or not, right? And the second thing we need to prove is like, well, they are convergent to the same point because that will leave us here. That will leave us to here. And the third thing we need to prove is like, well, they are convergent to the same point, and this point will be unique. Okay. So remember the three steps in the process, and now we can begin to talk about it. So first we can say because each interval in plus one is a subset of in, like becomes smaller, right? So an must be smaller equal to an plus one. And just because for all of the index an is smaller than bn, then n plus one is smaller than b, n plus one is smaller or equal to bn. And this is our starting point. This is the information we get at the beginning. And then we can find out, well, bn is a monotonically decreasing sequence. This is because like all of the in, remember the graph there? Like this is bn and bn plus 1, bn plus 2, and it will become more and more to the center. This is real line. So bn is a decreasing sequence, and an is a monotonically increasing sequence, right? And they must be converging at some point by the what we call the convergence monotone convergence theorem, because B is bounded by A. B is bounded by, or we say some value of an. Like if B is smaller than an, it's impossible because all of the Bn must be larger than an. And for all of the an, it is bounded by Bn. It cannot no longer go further than this point, or it will violate this assumption. So they must be convergent to some point. Bn, we suppose it converges to B, and An, it converges to A. So we have solved our first goal of proving like they are actually converging, which is a very exciting news. Okay. And what about next? So now we have, so now we already get a sense of, okay, they are convergent, right? So we can say, well, the next thing is like they are convergent to the same point. So then we'll use our second assumption here, which is the limit of Bn minus An is 0. And this will let I use the algebraic property from last lecture. Remember, like the limit of Bn minus An is actually limit of Bn minus the limit of An, and this will become B minus A by our definition above. So B is actually equal to A. Okay, so now we have proved our second point, like the limit of B and A, they're exactly the same. So now we are like two-thirds the way through. Okay, and now we can define because they're the same now. So we can define, well, X is their limit. Is their limit. X is the limit. And with one which is here, you can say X is in the middle of A and B. So X is in the range of I. Right. And then how to prove the uniqueness? We just like use our very traditional strategy. We define a new point, which is Y, and Y is not equal to X. Then what will happen is like Y is smaller than X or Y is larger than X, right? Because they're not equal, they must be smaller or larger than. And without loss of generosity, we can just say like Y is smaller than X and not considering another side. But here I think it's not we can use the without loss of generality, but not very necessary because we can also do because like the X is between A and B n. So if Y is in the range of In, then Y must be smaller than A or Y greater than B. Because like imagine if Y is equal to A, then Y is equal to X because X is in the middle of that, right? X can be in the middle of that. So so that's a violation. And remember what A and B means is like Y is smaller than the limit of An and Y is larger than the limit of Bn, which means, well, what will happen here is like, it will be larger than limit of Bn, which means like it cannot be X, but slightly here or slightly here. But if it's slightly here, A will not reach it, and B is go beyond this point. And if it's here, then A will go beyond this point, and B cannot reach that. And or we can say like in larger scale, this is our last IN, or we can say very, very large IN. I infinity is this one. And now what happens like this is some like not B. This is some A. This is some A very large. And this is some B very large. And Y is either in this side or this side, so cannot in the middle. Or that means like Y doesn't exist. So there only exists one value X that is the limit of both sequences A and B, and we're down here. And the nested interval theorem has a very important consequence following that, because what it exactly saying is like every real number or every point on the real number line can be approached by a sequence of real numbers. So there's no hole in the set of real number. If you can just pick one point and you can always find a nested a nested interval that goes smaller to that point, and it's still a real number. So there's no holes or no bricks, no bricks in the whole real number line. So that's the finding. Okay. All right. And yeah, we have talked about sequence, and we have, if you studied about like computer science before, you may familiar with the loop, and there are also something called nested loop, right? And and just remember the definition of the sequence. Like sequence is a function going from the natural number to more complex real number. And what about if we add a sequence on the sequence again, and then it will produce the subsequence? So subsequence is a function, is a nested function, or we can say a composite function. If you study the basics of function before, we can say we use two functions to represent a new sequence. So that's a subsequence. So if an is a random sequence and nk is another random sequence of natural numbers, and then it is strictly increasing. So this means like nk is a strictly increasing natural number. Okay, and now we define bk is equal to a nk. So this may looks confusing. So what this actually means is like we might just get rid of bk right now. Just remember, we can just use this one because this is a definition, right? So a n k, how we can interpret this one? First, we say nk. Nk is a sequence, so it has a fixed value. And another layer of the sequence is here. So now we have a fixed value of the index for a something, for the sequence a something. And the sequence a something, this index is determined by nk. So it's finally determined by k. And k leads to nk, and nk leads to ank. So that's a process of subsequence. Or maybe even more, you can say this is a n k m l g and goes like that. And finally, all of this multiple layers of subsequences will finally goes to g, because g determines this value, determine n, determine k, determine n, and then determines a. So it all goes back to a. Okay, and such ank or bk is called a subsequence of an. Okay, and usually, just as I said before, we just use the subsequence of an denoted as this one with the 3 layers of letters. Just means like nk is, just make sure like nk is strictly increasing. So why we need it strictly increasing? Because if it's not strictly increasing, we might met an index problem. Like we'll go from like, if it's not increasing, first we met a0, then we met a10, then we met a1. Then it seems like it's go back. So it doesn't make sense. Or it's a1 again. And this is not a sequence because this doesn't become how to say, become a doesn't become a function again, because this means we have 2 points in the same domain, and it goes to the same point. Or we can say, well, there's 2 points which is the same, right? A same point goes to 2 different values in the range, and this is not become a function, so it's not a sequence anymore. So strictly increasing, we must strictly follow that rule. And also the case term of this one is a and k. So now k becomes the index of the subsequence. But when we say about an, n is the index. But when we say about a and k, then k is the index. Okay. And there's an interesting lemma, and it's a very easy one. It's like if an converges to a, then every subsequence also converges to a. Well, this is very useful, because sometimes we may not find a sequence is converging to some point, but we can always find, oh, well, its subsequence is converging to some point. Then we can use because this is a lemma, then we can say, well, because a and k is converging to some point, that very likely that AN is converging to the same point. So we can use the subsequence to deduce back about the sequence itself. And the proof is very easy. We just use the definition of converging. So because AN converges to A, then there must exist an index N1 such that for all of the epsilon larger than 0, AN minus A is smaller than epsilon, right? This is the definition of convergence. And because Nk is a sequence of strictly increasing natural numbers, then for all of the index K, or we can say for all of the index N, because here I get the inspiration from a book called Advanced Calculus by Patrick. But then I figure out like, well, it makes some typos on the book. If it cannot be K, but we can say it's N. So for all index N, Nk is larger or equal to N because like N is a natural number. It's like go from 1, 2, 3, 4, 5, 6. And it's the least growing, strictly increasing sequence of natural numbers. And because Nk is also strictly increasing, it must be like 1, 2, it must be larger or equal to N because it cannot stick at least every step they increase once. So it will be equal or increasing larger, become 5, and it's become larger than that. And what's going on with increasing. So this one actually makes sense. So now we can say for all of the index K, Nk is larger or equal to N, larger than or equal to N1. And now Ank minus A, well, because it's beyond this point, it's beyond N1. And it's also smaller than the epsilon we defined, or for all epsilon we can find, which is positive. So Ank converges to A as a result. Yeah. So after seeing some proofs, we can see some like examples to help us understand. The first one might be, actually I want to give an example about subsequence at first. So A1, A2, A3, A4. This is a sequence. And about the subsequence, we define like Nk is equal to, well, we can say equal to 2 times K. And it becomes like Nk is 2 times K, so this is 2. A 2 times 2, 4. A 3 times 2 times 3, which is 6. And A 8. And this is a subsequence of this one. All right, so that's an example about subsequence. And for the real examples about subsequence and its converging properties and why it's converging to the same point, we can say we can use this lemma to find some interesting examples here. So first we can define Nk with, even though it's a function, it works well. And if we define Nk equal to N plus 1, first we can say this is a function and it is strictly increasing natural numbers. So Ank equals to An plus 1 is a subsequence of An, right? And by this lemma, we can say the limit of An is equal to the limit of An plus 1. This is a usage or application of the lemma above. So this one makes sense. Okay. And this is our first example. And it actually makes sense because An plus 1 is just one index further than An. So if it converges, and the plus 1 will become less and less effective or deterministic when it becomes very large. So that will solve it. Okay. And the second example is a usage of the lemma here, and also the usage of our first example. So first, we can define A1 is equal to 1. And we can use a recursive definition about subsequence here. And then we define An plus 1 is equal to 1 plus An divided by 2 plus An. Okay, so this is a recursive definition of sequence. We can first define the first term, and every term that is larger or beyond the first term has a, we can figure out the term one by one by one. So this is a recursive definition. And the interesting fact is like a plus 2, an plus 2, we can also write it as like okay, an plus 2, what is that? It depends on the an plus 1, so it's 2 plus an plus 1, 1 plus an plus 1. And we can also get a plug what n plus 1 into it, and we'll plug this into it. Okay. So we can always minus the terms, minus 2 adjacent or bounding terms one by one together to get this one out. Okay. But that is not the main focus here. The main focus here is we will use the lemma that why this is useful. Okay. Because AN is monotypically decreasing sequence. So how we can get that? Because AN is fixed value. And now every time like n is increasing 1, 2 plus an is larger than 1 plus an. So it becomes smaller and smaller. So this is monotypically decreasing, right? And each term an is positive. Is that right? Well, the first an is positive, and both the denominator and the numerator is positive, so it always positive. So an is bounded below, and because it's decreasing, it's bounded below, and it is converging. It is convergent to some number a. And by the property of convergent sequences, 1 plus an divided by 2 plus an is also convergent. So why this makes sense? Because remember, like the constant is always converging, like 1 and 2 are converging. And by the sum property of the convergence, 1 plus an is convergent, 2 plus an is convergent. And by the division property of the convergence, the whole thing is also convergent. And the convergence to this one, just use the linearity of the convergence. So we can solve it out. Well, but also remember from the last example, we also proved that the limit of an plus 1, which is a subsequence, is equal to the limit of an, and which is a. Okay, so we can do a limit by the equation an plus 1 is equal to this form. This is the equation, and the equation can always be taken limit outside of it too. And now it becomes an plus 1 when n goes to infinity is a, and this one is 1 plus a, this is 2 plus a, and finally what it actually say to us is limit of an is equal to a. And a, we can solve it from this function, and finally we get is 2 below root square of 5 minus 1. And that's the finding here. Okay. And one more theorem regarding the subsequence is every sequence have a monotone subsequence. So yeah. So let's first get some intuition about what this actually means. So it seems like sequence, when we talk about every sequence, it includes the divergent sequences and also convergent sequences. So divergent sequences can absolutely be very divergent, right? It can go like very fast, like the sequence of like oscillating and always increasing like that. Maybe it's not going back, but going to this way. So it is absolutely not convergent, right? But even the sequence like that can have a monotone subsequence. So now we're going to prove that. So, so for the proving process, we can first define a very interesting definition, which is what's called a peak index. So peak index is defined by the value that is the peak of the whole sequence. So peak is always exist, right? For example, we can say like the peak index is the largest. It's the largest point that is for all of the number that goes beyond it, and it is the largest one. So in this case, we're going to say, well, this when like the peak index is n, what does n mean? So like this is peak, this is peak, this is peak, and later it is all within that peak. Peak can be infinite as well. Like if peak is infinite, it can always be infinite, because if the number goes like that, and the peak is maybe not like that, but yeah, it goes like that. It goes to very large, and peak will be the infinite. The peak index is infinite, and it means like, well, it reaches infinite. So that's the peak index definition. And what we'll talk about here is we are divided into two cases. So first, if there are infinitely many peak indexes, this is likely to happen. For example, the sine function or function here, it can have multiple peak indices at the same time, because when both of the all of the three values here are actually the same value, then they are both the peak indices. Or another good example is the sine function, right? Sine function have infinitely many peak indices at one, and also have many of the trough indices at the lower one, at negative one, negative one, negative one, and this is 1, 1, 1, 1. So we can have infinitely many peak indices. And if this happens, then nk will be we can always like pick nk to be the case peak indexes. And now a nk will be a monotonically increasing sequence or monotonically decreasing sequence, because every term is the same. It's the peak index, which means their value is the same. So we have actually find the subsequence, which is monotone, right? And what about the second one? What was the second one? There are only finitely many peak indices. So maybe like this one, it only has 3. So after that, it becomes smaller and smaller. So we can use one algorithm to do that. There's some other ways to prove this, to prove the second case in many different books. I see some examples, like some using to prove it's actually monotonically increasing or decreasing. Both is okay. But here I want to introduce one way of like I innovatively designed. I designed this way to prove like we can always pick a subsequence that is monotonically decreasing. So what I do is like for all of the indexes, which is greater than some n1. So first, let's define like n1 is some value which is very large. And when it's greater than that, the n2 will be the largest peak index in the range here. So maybe this is n1, and we can always pick n2 here. This is n1, okay, pick n2, and this is go beyond n1, this is the largest. Because it's like finitely many, so there must be a largest index here. And maybe like when we pick n2, and then we pick the indexes here, right? This will become n3. Okay, and this is n4, n5 too, if they are the same. And it will always, because this is a peak index, which means that all the values smaller than it. If it is a peak index, all the values smaller than it. And finally, if we reach some point that actually have infinitely many peak indexes at the same time, we just pick them as our final, how to say, like the final we'll return to this one again. So there will be like A1, A2, A3, A4, maybe from the fifth layer, they will have infinitely many peak indices larger than N4. And now we'll pick all of those peak indices again to be our final infinite many terms in our sequence. So the algorithm finally goes into that. So once it reach like for all index K contains infinitely many peak indices, and then define and k plus 1, k plus 2, k plus 3 be the k plus 1 to infinite term in this sequence. And now a and k is a monotonically decreasing sequence because it's always decreasing in this trend. Okay, and there's a corollary regarding this one. It's called every bounded sequence have a convergent subsequence. Well, so what's the connection between that? It's like the theory is like every sequence have a not monotone subsequence, and every bounded sequence have a convergent subsequence. So why this is a corollary of this one? Because it just adding another theorem into it, which is the monotone convergence theorem. Because that theorem says like a bounded sequence, a bounded monotone sequence is always convergent. So every sequence have a monotone subsequence. So every bounded subsequence, like if a sequence is bounded, all of its subsequence is also bounded because subsequence is a subset of sequence, the value in sequence. And because it's bounded and because it's monotone, then it is convergent. All right. So I think there's not too much problem regarding this definition. And then we'll see some definition regarding which is I think new to you. And one is called sequentially compact, and another is called compact. And such definition is very similar to what we define what you have heard about closed sets before. So you can think about it as closed to easy understanding at first, but finally we'll find out like it's actually different. So the first is sequentially compact. So for a set S, if S is a subset of real numbers, it is subsequent if like for all of the sequence that is that is taken value from the set S, AN has a subsequence that converges to A. Converges to A, or it converges to some point that is in the set S. Okay. So what does this mean? So first we can see some examples. Is S1 a sequentially compact set? Well, first we can say let's define AN equal to N, and this sequence is in this S1, right? Because it goes from 1, 2, 3, 4, 5, 6, the natural number set, which is a subset in this, in S1. And if this set is sequentially compact, then this sequence must have a subsequence that converges to a point in S. Well, but here, AN is natural number. It does not convergent. It's actually divergent, or it converges to infinite, which it doesn't exist. So yeah, so it is divergent. So the subsequent have the same converging point as the original sequence. So every subsequent it converges to it diverges to, right? It diverges to. So S1 fails to be sequentially compact. The second example is like if S2 is going from 0 to 2. This one is also not sequentially compact because, yeah, a very famous example using 1 over n, you can find out like 1 over n is a sequence here, but it converges, it does converge, but it converges to 0. And 0, well, what about 0? 0 is not in this set. 0 is not in this set. It's outside of from 0 to 2, and 0 is not included. And because every subsequent have the same converging point as the original sequence 1 over n, and every subsequence also converge to 0 and it's not in it. So this one is also not sequentially compact. And one interesting to notice, like both of these 2 points, both of these 2 sets, this one is not closed set. What about like 1, 2? Leave as an exercise for you to find out. Like if 1, 2 is a sequentially compact set. And yeah, it's a way to think about like first, intuitively it is a closed set, so it's very likely to be sequentially compact. And then to prove it, you need to find like for all of the sequence that in it, it converges to the point that it converges to a point actually in it. First, it will be convergent. Second, it is the converging point is in the set. And I think it's an easy exercise for you. Right. And now we reach one very significant theorem in math history. It's called BW theorem, or Bolzano-Weierstrass theorem, or we can also say it's the sequential compactness theorem. This theorem says like all of the form of the closed set AB, like the closed set AB, if A is smaller than B and AB are real number, is sequentially compact, which indicates our discussion here is correct. Like 1, 2, well, 1, 2 is actually in this form, so it's sequentially compact. So how can we prove it? So actually we can prove it by using the by using the definition of sequentially compact and also the monotone convergence theorem. Okay, so first we set a arbitrary sequence an in AB, which is within it. We can see the definition here. Well, an is any sequence that is in the set S or in the set AB here. So an is bounded because AB is bounded, and all of the value of an is taken from AB, so an is bounded. So because an is bounded and it is bounded, it's a bounded sequence, and the bounded sequence always have by the corollary here, every bounded sequence have a convergent subsequence. So it must have a subsequence which is convergent. We denote it by this one, by the A and K. So this is convergent subsequence of it. Okay, and because A and K is also belongs to this set, right? And remember from the last lecture, we proved like if a sequence in AB and Cn converges to C, and C, then C is also in AB. So which means like this one is a convergent sequence and is in the set, it belongs to AB, then its convergent limit, or we say converges to K. K is also belongs to AB. Well, so we're satisfied with our with the definition of sequential compact, because for all of the subsequence A and K, its limit, it converges, its limit point is also belongs to AB. So AB is sequential compact. Another interesting theorem is like that: is if S, a subset of real number, is both closed and bounded, then S is sequentially compact. Okay, so what closed means is like as we discussed before. Closed, it means like every so what closed discussed is like for all of the sequence in the set, the limit is also in that set. So this is the closed definition. And what bounded means is more it's even more obvious. It's like, okay, it has a lower bound and it has a greatest lower bound and it has the least upper bound. Then it's bounded. Okay. And now let's say let's figure out if this actually makes sense. So if an is a sequence in S, which is bounded, okay, and because it is bounded, then there exists a sequence A and K, like which is convergent, and it convergent to a point in S. And this is and what this is actually mean. This is from the sequential compactness theorem. So yeah, so it is actually in that set. Or we can say this is a how to say, sequencing S. Yeah, this is sequencing S, and the converging point is also in S. Yeah, because it's yeah. This is not because the BW theorem. It is because it's mainly because it's closed. So closed means it's yeah, it's a limiting point is in the set. Okay. All right. Then it is bounded, it's convergent, it's closed, it's infinite, then S is sequentially compact. And then we are solving this proof of the theorem. Okay, so now some important theorem we want to recover it. First is if a set is both closed and bounded, it's sequentially compact. And this can be if and only if relationship later as we find out. And also every set in the form of A, B, and looks like a closed set is actually sequentially compact. And also every bounded sequence have convergent subsequence. And every sequence have a monotone subsequence. So, and also at the beginning, we have proved like, we have proved here, it's like, if a sequence is in the form of C to the power of N, then we can easily figure out whether it is divergent or convergent. So this is the finding for today so far. Now I will want to give you some new definitions in mathematics, which is called cover. And this branch is a relatively unimportant portion for next day's lecture, for the next lecture, for the continuity of function, but it is very helpful in topology when if you want to study topology or study about the major theory, and this part is very important. So maybe I will spend some time to discuss it. Okay. So first, what is cover? A cover is, you can just think about, it's a collection of set. It's an infinite cardinality collection of set that can cover all of the elements in another set. So the precise definition is here. It's like for all of the element in S, there exists an N such that S is in the set of Sn. Then we can say the sequence of Sn, or the collection of Sn, goes from n to 1, n equal to 1 to infinity, is a cover for S. Or because this is very similar to what we call a union of infinite union of set, we can always denote it in this form, like Sn, the union of all of set Sn, S is a subset of it. So this is a definition of cover. Okay, and what is a finite subcover? Remember here, cover is defined on set, like a set has a cover. For example, we can say, yeah, we'll see some example here. So first we can say, like, if S is equal to, yeah, we will see that example later. We'll first talk about subcover. So subcover is defined on cover, and the cover is defined on set. So we can say, if we have a set S, then if we can figure out, well, there is a sequence of set Sn such that its union and goes from 1 to infinity, and S is a subset of that set. Then we can say, well, S is a, let's say S is a subset of that, and Sn is a cover for S. And what a finite subcover is defined on Sn. It's defined here. So subcover is defined here, which means, like, if there exists index n such that S is now not belong to the infinity one, but belongs to, like, n goes from 1 to n, and there's a fixed index, there's a finite number of set Sn in the sequence of Sn that already cover S. Then this n leading term, like S1, S2, S3 to Sn, this set is called a finite subcover of the cover Sn for S. So that's the definition of the finite subcover. Okay. Then we'll see some examples. So there are actually just one example. So let us denote the set S is in the range like going from A to B and is closed. However, S is not equal to C and C is in the range of A to B. So this one can use a graph to represent like this is A, this is B, and this is the set S. This is set S. However, C, if this is C, and C is not in S. C is not in S. Okay. So this is the set we define for S. And what we can find out is like we can define a cover for S first. Okay. So IN can be a cover. IN is defined by C minus N, C minus from C minus N to C minus 1 over N, and C plus 1 over N from C plus 1 over N to C plus N. Okay, so what that means is like this is C and C minus N maybe here, like C minus N, or give them a C minus 4, and this is C minus 1 over 4, and oh no, not 4, but yeah, not 4, maybe 5, because when it's minus, it's odd, right? So this is 5, and this might be plus C plus 1 over 6, C plus 6, because when it's even, it's plus. Then when 5 and 6 goes to infinity, it becomes very close to C, and this goes to negative infinity, and this goes to infinity, and this one will very close to C. So this is a by Archimedean property. Remember, like for every epsilon larger than 0, there'll always be a 1 over n, like smaller than that, and always be n larger than any value which is very, very large. So the union of all of the IN becomes the set X not in C. So this is the, okay. So now this condition is satisfied for this condition. And there's 2 more conditions here. And this 2 more condition, which means like this is S is a subset for this one. So S is a subset of that one, which means like IN is a cover for S, right? So this is an example of cover. However, well, this one might not have a finite subcover. So why is that? Because we cannot find a index n such that C plus 1 over n to C plus n. And this set, well, this set cannot contain all of the like the elements in S. For example, we can pick a very, very large n such that well, we can look like that. Okay, suppose like we pick a n which is pretty large. So now this C, this is A, this is B, and n contains this part. Is go beyond A and B. But however, this is what we call this point here. Is what we call C plus M plus 1, right? However, there's by the Archimedean theorem, there can also be a point. There is a point which is called C plus M plus 1 over N. And this one is in the set of S, but not in the set of this one. So it fails to have a finite subcover. So which is like a very unfortunate case for us to see. So see, that is a very common strategy to prove some cover doesn't have a finite subcover. If you can find an opposite example of that. And finally, we can give you a definition of compact. So compact, what compact means like a subset S of R, like, or we can say S is any set constructed by a real number, is compact if for all cover of S. Like, yeah, we can say we can give you example like this is the set S. This is set S. It's in the real number line, right? And well, and this is a compact set if all of the sequence within it, or maybe not sequence, okay. You can see like all of the cover for S, which is constructed by open intervals, or there's like open intervals sequence, which is let's say uh, a cover for S, because you add like I1, I2, I3, I4, I5, I6, and it goes along the way. And finally, you will reach a point. You will reach a point like it covers S already. And for all of the open interval cover of S, finally, we can always find a finite subcover for such IN. For example, in this example, I1, I2, I3, I4, I5, I6, the n equal to 6 is a subcover because 6 from 1 is already covered S. So this is a definition of compact. Or we can use another more succinct way to write it. It's like for index in is the open interval and in is this relation means in is a cover for S. Then there always exists a n index n such that S is a subset of union from n to 1, n to 1 to n. I like always have a finite subcover. So this is compact. So compact, yeah, compact is actually means it is closed, and also it can it just means like a closed set. And actually, when we only talk about like real numbers, we are limited in real numbers, then compact, if and only if S is compact, then S is both closed and bounded. And if and only if S is sequentially compact, then S is compact. So first compact, second sequentially compact, third bounded and closed. Those three concepts are equivalent to each other in when we are only talking about the real numbers. However, in higher dimensions, which means like there's more because real number is one dimension, but in n-dimensional cases, in topological examples, it might have some difference between them. Well, but for now, they're all equal. And that will be our final conclusion for today. When we have discovered compactness, sequential compactness, and boundedness, closedness, and absolutely sequences and subsequences, monotone sequences, all in this three lectures. So a large bunch of information for you to read the books and do some exercise to get prepared for the next one. Okay. And the final thought about the second statement here. This is also called Hien-Borel theorem. Or we can say like a closed bounded set of R is compact. Yeah, this is called the Hien-Borel theorem. Okay, not the second one, but maybe the first one. So we'll see this later on. We'll see this later on. Maybe next summer, maybe the summer after the next summer, when we talk about the topology, we'll meet this theorem again. And finally, I want to give you some look at the proof for 2. Just because I don't have time for today, but you can pause the video and to look it carefully. And that's the proof for the second statement above.